Hi everyone, so today we're going to be actually talking about special right triangles, but to do that, I thought we'd just look at this really special figure we've been talking about, the square, okay? So the square. What do we know about a square? Well, we know that it has 4 equal sides. We know that it has 4 right angles. And what's really interesting about the square, when we've been working with the Pythagorean theorem, is we know that if we draw a diagonal in it, that blue line is called a diagonal, then we can actually use the Pythagorean theorem, because now we've broken it into 2 right triangles. We actually could make it 4 right triangles, but I'm just going to draw on that one diagonal. Now, what we also have done is I've given you some squares. So let's just take a second, and I've given you some squares that I've had. Let me put in a diagonal. I put in maybe side length 2, and you've used the Pythagorean theorem, and you've done 2 squared plus 2 squared equals d squared for the diagonal, and so 4 plus 4 equals d squared, and so 8 equals d squared, and there we've taken the square root of both sides, remember that? And then we've simplified root 8 into 2 root 2. Okay? Then we've also worked with squares where I've given you the sides are x, and maybe the hypotenuse of that right triangle inside the square, maybe that diagonal, maybe I said it was like 8. And so those were a little bit harder because you had to recognize that it was x squared plus x squared equaled 8 squared. You had to combine the like terms, and remember that when we combine like terms, we never change our power, so it would be 2x squared equals 64, and then you divided by 2, getting that x squared equaled 32. All right, and then we took the square root of both sides, giving us, this could be root 16 times root 2, so 4 root 2. So these both would then be 4 root 2. All right, so that's some of the things we've already done, but I kind of want to think of this square as like such a special figure. That triangle you're creating when you draw in the diagonal, let's think about it. It has 2 congruent sides. Well, we know at a minimum it's a right triangle, right? A right triangle. But what do we know about a triangle that has 2 equal sides? Well, I'm hoping that you're saying to yourself, Coach Fred, that's silly, you know it. It's isosceles. So we actually call this triangle, we call it an isosceles right triangle, and it's really special. Remember, we've talked about that the square is really special. Square is really special for a number of reasons. Like, we've got all different shapes in it. We even could take a circle and put the circle around it, kind of like that, where the circle is tangent to the square is tangent to the circle, meaning it touches it in all the 4 corners. And we can see that that diagonal of the square is actually the diameter of the circle. So the square is just so cool. Well, when we draw on that diagonal, it breaks it into an isosceles right triangle. That tells me even more. Remember, if it's isosceles, then each of these angles is congruent. Remember, the angles opposite the congruent sides are congruent. Well, wait a second, I know even more. If this is a 90-degree angle, then these 2 angles also have to be 90. And if they're equal, and I divide them into 2, then each of those angles are 45 degrees. 45 degrees. Again, you're still not really taking notes, we're just reviewing. But that actually creates what this lesson is about. It creates a triangle called a 45 5, 45, 90 triangle. And just like all of our shapes have these cool relationships, this one does too, okay? So again, we call it an isosceles right triangle, also known as a 45, 45, 90 triangle. And that's where our lesson is going to start today. So we're going to look at a 45, 45, 90 triangle. It's the 8-4 notes. All right, so we're going to be given a square with side lengths of 5. So here's a square. I'm going to mark all 4 sides congruent. It wants us to find the length of the hypotenuse. Actually, it should say length of the diagonal, which is the hypotenuse of this right triangle. Okay? Now, I'm going to use the Pythagorean Theorem. So 5 squared plus 5 squared, I'll put a d here, equals d squared, and 25 plus 25 equals d squared. All right, so that's going to give me 50. Now notice I'm adding the exact same value both times because they're equal, and then I'm going to take the square root of both sides. I'm going to simplify, and we're going to see that there is a 25 and a 2. Now look at that. You added 25 and 25, which is doubling 25. And you can see that the factors of 50 are 25 and 2. All right, I take the square root of both sides, and I get 5 root 2 equals d. All right, now, some of you might recognize from what we just did that when we had side lengths 2 and 2, that our hypotenuse worked out to be 2 root 2. I wonder if that relationship happens every time. So let's look at see if we can identify a pattern. Here are some isosceles right triangles that I've created for you, and I've solved them all. I want you to take a minute and write down 3 things that you notice or wonder. Notice or wonder. Press pause and try. All right, you're back. And so I'm hoping that you maybe noticed that all of the legs were equal to each other, like 7 and 7, 3 and 3, 5 and 5, 1 and 1, 4 and 4, 2 and 2. Wondering if you noticed that they were all isosceles. Did you notice they were all right triangles, maybe? Maybe you noticed that the hypotenuse of the triangles was always the sides times root 2. And maybe you noticed that there were 45-degree angles. Maybe you wondered if in every right triangle that was isosceles, if you knew the sides, then you could just multiply by root 2 to get the hypotenuse. Well, that's actually the relationship that I wanted you to see. If I generalized in a right isosceles triangle, an isosceles right triangle, if I generalize the sides, if the sides are x and x, again, it's a 45, 45, 90 triangle, then the hypotenuse's length would be x root 2. All right, we're going to pick up from this tomorrow in class. We're going to do some investigation as to why that works. And we're going to look at when the hypotenuse is a whole number. Hopefully this was helpful. Have a great day.